Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Quasi-Steady Analysis of Simultaneous Heat and Mass Transfer Part 2. In this lecture also we will be taking two problems which we will be studying or analyzing using pseudo steady state analysis or quasi steady analysis. The first one is freezing of salt water. So, here this problem involves a simplified model for growth of ice crystal in salt water. We have a ice crystal of certain radius r, and then it is in a salt water. So, the purpose is that the growth of this ice crystal, how is it going to take place in salt water? That is what we are going to have the problem. So, in that case, so if we in order to know the change in radius with respect to time, etc., how to do the analysis. If you wanted to know the temperature profile, etc., in the liquid phase, then how to do all those analysis, that is what we are going to do here. Crystal which is pure H2O is idealized as a sphere of radius capital R function of time t. That means it is increasing as growth of crystal is taking place. Main effect of salt is that it lowers the freezing point. Whatever freezing point T suffix F is there, that would be lowered if you add or if you do this crystallization in salt water rather than in pure water. Right. Freezing point depression is described by Tf is equals to T naught minus beta C suffix S, where T naught is freezing point for pure water, beta is known positive constant, and Cs is salt concentration. Okay. So, this T naught is freezing point for pure water, right. But this crystallization or growth of ice crystal, whatever you wanted to do little rapidly faster. So, then rather crystallizing in pure water, what you do in salt water. So, that by using that salt water, this freezing point will decrease, and then the depression in freezing point is given by this expression. Far from crystal, the temperature T infinity and then concentration C infinity are known, and then solution is stagnant. That is the other condition. So, these things are known to us, C infinity and T infinity are known, which are far away from the crystals. Assume that temperature and concentration fields are both pseudo steady and spherically symmetric. When we say spherically symmetric, then what we can say, whatever the changes in species concentration because of species conservation, and then change in temperature, etc., because of solving the energy equation that we get, all those things would be varying in only r direction. So, we do not need to worry about theta and then phi direction variations. We need to worry variations in r direction only, as long as the sphere is symmetrically spherical. For simplicity, assume that ice, pure water and salt solution all have the same density. So, rho I, rho W, rho L, all these are equal to each other. That is what it means by notations. I we are using for ice phase, W for water, S for salt alone, L for salt solution. Okay. So, they are different. Fine. Now, the first part of the question is, we have to prove that Vr is equals to 0 throughout the fluid by simplifying the equation of continuity. Then second part, assuming for the moment that no salt is present, that is you are taking pure water, then what is the expression for dr by dt, how this r is increasing with respect to time because as the crystallization process continues. Now, for case of salt water, note that temperature and salt concentration in liquid at r is equals to capital R are both known, right. So, temperature and then salt concentration at the surface are known, and as is dr by dt. Use the conservation of salt to obtain one relationship among these quantities, that is among dr dt, T naught and then Cs at the surface, etc. For these relating these quantities, you have to develop one relation. Then use conservation of energy To obtain second relationship among these quantities mentioned in part C of the problem, assume that partial molar enthalpies in the liquid are constant. Assume that temperature variations in the liquid produce enthalpy changes which are negligible compared to the latent heat lambda. Describe how to compute the calculation of dr by dt for salt water, that is the last part of the question. So, we take one by one as we have done in the previous 2 lectures and then try to obtain these things. Problem looks lengthier, but the sequence when we go step by step, it looks very simple and straightforward because we have already done couple of problems like this. So, schematically if you take the system, we have a spherical crystal whose radius is capital R initially, and then it is function of time, it gradually increases. This crystal is of pure water, okay, and it is in a salt solution. Far away from the crystal, that is at R is equals to infinity, T infinity and C infinity, that is temperature and then salt concentration are known at far away distance from the crystal, right. Now, freezing point depression, this is what is given, this is C suffix S, Tf is equals to T naught minus beta multiplied by Cs. Cs is salt concentration. Now, we use equation of continuity to show that Vr is equals to 0 in the liquid. So, continuity equation, Vr, now we understand only r coordinate variations are only there because of the spherically symmetric condition that is given. So, theta and then phi will not be taking for anything, whether it is conservation of mass, conservation of momentum, conservation of energy or conservation of species transfer, whatever is there. So, we take only r coordinate variations because it has been mentioned in the problem that symmetrically spherical crystal is there, and then under such conditions this Vr or temperature or concentration variations whatever are there, they will be function of r only with respect to the space, but in addition to the space it is also dependent on the time. So, Vr as function of r and t we have to find out, and then when the density is constant. Why constant? Because it has mentioned that the densities of all three are equal. So, continuity equation, if you write, we get dou in spherical coordinate dou by dou r of r square Vr is equals to 0 plus 1 by r sin theta dou by dou theta of V theta sin theta would also be there, plus 1 by r square sin theta dou by dou theta of V phi sin theta, these terms should also be there, but we are not taking these terms, right. V phi terms or theta terms we are not taking. So, that is the reason we are writing only this part. Okay. This we understand by this now because we have already solved so many problems. So, in the continuity equation I am writing only the term which is having r coordinates or the function of r, that term only we are writing. V theta V phi terms I am not writing because it is clearly mentioned, and then we have already solved so many problems, we know how to do that one. So, we get dou by dou r of r square Vr is equals to 0, that means r square Vr is equals to constant, but that constant is function of time, that constant is function of time, but it is independent of r, okay, independent of space, but dependent on the time. Okay. So, if you apply boundary condition at r square at r is equals to capital R, then again we get the same thing, capital R square Vr at capital R comma t is again Ft. Okay. So, but now this from here we cannot prove that Vr is 0 everywhere. So, we have to leave it as it is. Now, but we write conservation of mass at the interface, that at r is equals to r, right. So, then towards the crystal side whatever is there, that we are writing r minus, towards the liquid side whatever is there, at that we are writing r plus. Both of them are at the surface only. Towards the crystal side we are writing indicating r minus quantities, or towards the liquid side we are writing quantities at r plus or r plus quantities, or I or L whatever we are taking. So, rho Vr minus rho dr by deta in the ice is equals to rho Vr minus rho dr by dt in the liquid, right. In the ice there is no velocity, so Vr is 0. Now here rho I, this is rho I, this is rho L, this is also rho L. So then what we get by applying the stationary solid ice, Vr is 0, then remaining part ice density you write rho I, and then that of liquid you write rho L, then simplify, then you get Vr is equals to rho L minus rho I divided by rho L dr by dt, and then that should be 0 because rho L minus rho I is equals to 0, because in the problem it has been mentioned that densities of all three are equal to each other. So that means Vr is 0 in the entire liquid. Okay. So that is the first part is done. First part is done, that we have to show Vr is equals to 0 in the liquid. Now we take the second part of the problem, determine dr by dt for pure water case when there is no salt. When there is no salt added to the liquid, then it is a pure water. So then Cs is 0 because Cs indicates the salt concentration, right. For pure water with Vr is equals to 0, then energy equation E if you write, you get only this Kw dou T by dou R, or Er would be having the only conduction terms, other terms will not be there, right, because the Vr is 0, so the convection terms are anyway not there. Okay. And then system is so small, there is no velocity etc. So the viscous dissipation etc. all those terms would also be not there, or work done by pressure etc. those terms are not there, right. The simplified energy conservation equation for liquid if you write, that is dou by dou R of R square Er is equals to 0 would be there, right. In spherical coordinates, you write energy equation in terms of E quantities, that is Er, E theta, E phi etc. So then E theta, E phi are anyway not there, and then Er terms are also only with variation with respect to R direction are there, that also only conduction terms are there. Now convection side terms are not there because Vr is 0. Right. So then we get dou by dou R of R square Er is equals to 0, right. Now again here again if you integrate R square Er is equals to, you will get a constant, but that constant is function of time. It is a constant with respect to R, or with respect to space it is a constant, but with respect to time it is function of time, some unknown function f of t. Let us not worry about what it is. So now from this equation what we can write? We can write dou T by dou R is equals to minus Er by Kw, right, and then from here we can write Er is equals to minus, Er is nothing but Ft by R square, and then minus and divide by Kw as it is, right. So this if you solve, you get the temperature profile. Okay. So now this equation we integrate first, okay, then we get T is equals to f of t divided by Kwr plus another constant g of time. So this is also constant with respect to r, but it is function of some function of time. What it is we do not know, right. Now we have two boundary condition. It has been mentioned that at the surface the concentrations are known, far away concentration are anyway known, that both of them at the surface temperature is known, and then far away from the crystal surface also at r is equals to r infinity also the temperature is known, that is given. So at r is equals to r infinity, T is equals to T infinity is given. If r is equals to infinity, that if you substitute in this equation, so 1 by infinity is 0, so then first term is gone, so T infinity would be equal to Gt, right. Other boundary condition at r is equals to r, T is equals to Tf, freezing point, which is given as T naught minus beta Cs capital R comma T, but it is a pure water. Pure water case we are doing problem B, problem C is for the salt water case. So for problem B pure water, so salt concentration is 0, so Tf is nothing but T naught, and then this you substitute here, so you get Ft by Kw capital R plus Gt. So, that is Ft by Kw capital R plus Gt is nothing but T infinity from the first boundary condition. So, Ft by Kw we can write capital R multiplied by T naught minus T infinity. So, that means this Ft by Kw is now known and then Gt is also known to us. So, Ft by Kw is nothing but capital R multiplied by T naught minus T infinity, and then this all divided by R is there, and plus Gt is nothing but T infinity. So, this is the relation for the temperature as function of time. You may be thinking that right side everything is function of R, there is no time function. So, that is not true, because this R whatever is there, that R is function of time. So, that is the reason here also we have written T as function of R comma time T. Okay. Now, use energy conservation equation at interface to relate T to dr by dt. Actually, our purpose of question B is not to get the temperature profile, but we have to get relation for dr by dt, and then that relation that should be related to T. What we have done now, T we have related to capital R, but we have to relate T to dr by dt. So, that is the reason we are writing energy conservation equation at the interface. So, now crystal side ice we are writing W, and then water side liquid side, now it is pure water. So, then W we are writing. So, ER minus sigma Ci Hi bar dr by dt towards the ice side should be balanced by ER minus sigma Ci Hi bar dr by dt towards the water side should be balanced at interface, right. So, now this ER is nothing but minus K dou T by dou R. Now, again we are replacing this I by R minus just to indicate that it is towards the ice side, and then this W we are replacing by R plus indicating towards the liquid side or water side now, because it is a pure water. So, this we can write ER is nothing but only conduction term is there here, no other contribution is there, convection term and then viscous dissipation contribution etc. are not there. Whatever because of the concentration or enthalpy changes etc. are there, we have already written them here. So, ER is having only conduction contribution, that is minus Ki dou T by dou R at R minus this Ci Hi bar dr by dt as it is. You may be thinking that what about that NIR or NIX terms, in this case NIR terms or NSR terms etc., why they are not coming? They will be coming if you have a dilute system or more than one component is there. Now, it is two phases, but only one component H2O, pure water and then water crystal made of pure water. So, those other terms are also not coming into the ER terms. They will be coming in the C problem, where we are doing the same this B problem for the case of salt water or salt solution, right. So, this is what we have. Now, towards the this right side also, what we have in place of ER, we have only minus Kw dou T by dou R, and this is Cw Hw bar dr by dt. There is no summation because only one component is there. Okay. So, now towards the ice side, temperature is constant from the center to the interface. Temperature is constant in the crystal, obviously it has to be. So, that is the reason dt by dr is 0. So, now what we can write from here, minus Kw dou T by dou R is equals to Cw Hw bar dr by dt minus Ci Hi bar dr by dt we can write. So, that we have written here, right. So, but this dt by dr at R plus. Okay. Now, this molar enthalpies we have written, the concentrations are not known, Cw, Ci etc. are not given, but rho is given. So, that is the reason this molar enthalpies, partial molar enthalpies we are writing per unit mass enthalpies, specific enthalpy. So, rho W Hw tilde minus rho I Hi tilde, bars for the partial molar and then tildes per unit mass, okay, and then this dr by dt. Fine. So, now densities are also constant, it has been mentioned. So, that we can take rho w and then multiplied by this one. So, now the change in enthalpies whatever are there because of the temperature variations are shown in the left hand side. So, the change in enthalpies are very small, that is had been mentioned. Compared to the latent heat, this change in enthalpies is very small. So, then this we can replace by lambda here. So, we get minus kW dou T by dou R is equals to rho W lambda dr by dt. So, dr by dt relation we want. So, that dr by dt we are keeping one side, rest everything we are writing other side. In the previous slide we got t is equals to r t as function of r comma t, we got it as t naught minus t infinity multiplied by r function of time divided by small r plus t infinity we had. So, if you do dou t by dou r here, you get t naught minus t infinity minus r by r square at r is equals to capital R. So, that we have written here, right. Capital R, that is function of time. So, as it is we are writing here. So, this equation we can write, when you substitute small r is equals to capital R, you will get 1 by capital R. So, that is kW by rho w lambda r multiplied by t naught minus t infinity. This is the relation for dr by dt. Okay. Now, the same thing we do by taking a salt solution. Okay. Till now we are taking ice crystal in pure water for the problem B. Now, for problem C, that same pure ice water crystal whatever is there, that we are taking in salt solution, because by adding some salt, depression of freezing point is taking place. So, crystal growth can be a little faster. Okay. So, for that case, what is dr by dt, that we have to do. Species conservation equation for salt solution we write, you get dou by dou r of r square NSR is equals to 0. That means r square NSR is equals to constant, which is function of time, but independent of r. With respect to r it is constant, but it is function of time. Okay. So, this we are getting here also ns theta and then ns phi etc., those terms should also be there, but we are not writing them. Why we are not writing? Because we already know that spherically symmetric system is there. So, variations are there only in r direction, theta and phi direction, those variations are not there. Boundary condition at r is equals to capital R, it has been mentioned that the flux is known. Let us say that flux is NSR at capital R comma t, right. So, that means small r square n small r at small r comma t is equals to function of f of t, that should be equals to capital R square NSR as function of r comma t. Now, this equation is also of no use until and unless what is this relation that we find out, what is NSR as function of small r comma t, that is what we have to find out, then only we can use this equation. So, for but dilute solution with VR is equals to 0. If VR is 0, that means there is no bulk motion. If there is no bulk motion, in the combined flux you will be having only diffusive flux terms only be there, right. So, due to the bulk motion whatever the flux contribution is there, that is not there. So, that is NSR at NSR as function of small r comma t is nothing but minus ds dou Cs by dou r, because VR is equals to 0 in the liquid, that we have seen problem A. From problem A, we have already proved that VR as function of r comma t is equals to 0 in liquid. So, in the NSR only diffusive flux contribution would be there, convective flux contribution would not be there. So, NSR at small r comma t is minus ds dou Cs by dou r. This is again still not complete, because what is this Cs function of r, that also we do not know. So, for that reason we have to go for interfacial balance equations anyway, that we will do. So, from this equation dou C by dou r we can write minus NSR function of r comma t divided by ds. NSR at r comma t, from this equation what we can write, NSR at capital R comma t multiplied by r square by small r square we can write, and divided by ds is as it is. We get Cs is equals to NSR, this is at capital NSR at capital R comma t. So, it is a constant, it is changing in radial direction, but at the interface it is constant. So, we have to treat it as a constant divided by ds, and then capital R square, and then integration of minus 1 by r square is plus 1 by r plus constant, integration constant, that is constant with respect to r, but it is constant, that constant whatever is there, that is function of time. So, capital GT we are writing. So, this we have to find out. We know at far away distance from the crystal, that is at r is equals to infinity, concentration of salt is known, that is C infinity. So, here if you substitute r is equals to infinity, then Cs would be C infinity. So, that means G t is equals to C infinity, because 1 by infinity is 0 here. So, G t is equals to C infinity, that we know. So, what we get from here, Cs as function of small r comma t is nothing but given by this expression, right. Now, use species conservation equation at interface to relate Cs to dr by dt, because the previous equation Cs as function of small r comma t that we got, and then that is in terms of r as function of time is there, right, in this slide here. So, now here Cs is related to r, right, this r is related to time, but we want this Cs related to be dr, related to dr by dt. So, that we wanted to do. So, that we can get here by using the species conservation equation at the interface. So, now here you can see NSR minus Cs dr by dt towards the ice side should be balanced by NSR minus Cs dr by dt should be balanced by liquid side, right. So, in the ice side, ice the crystal whatever is there, ice crystal is there, of it is pure water. So, Cs is 0. So, if there is no salt in the crystal phase, so then obviously its flux would also be 0 in the crystal side. So, what we have here, NSR is equals to Cs dr by dt. So, now this Cs as function of small r t we know, but now here it is as function of capital R comma t, that is what we have. So, the previous slide what we got, Cs at small r comma t, we got it as NSR at capital R comma t divided by ds and small r and capital R square by small r was there. So, in place of this small r you are writing capital R, because you want Cs at capital R comma t. So, in the previous expression, previous slide, whatever Cs at small r comma t was there. So, this r you replace by capital R. So, get Cs at capital R comma t. So, then we have this one. So, that is this one, right. So, what we have here, Cs capital R comma t is equals to Ns capital R comma t divided by ds, r plus C infinity was there, but NSR capital R comma t we do not know, right. So, what we know, it is nothing but Cs capital R comma t dr by dt. So, Cs capital R comma t dr by dt in place of NSR at capital R comma t that we have written, and then remaining this r divided by ds plus C infinity terms are as it is, right. Then what you can write, Cs r comma t terms one side, the remaining terms other side, if you write, you get the relation between Cs and dr by dt by given by this one, fine. So, now here C at capital R comma t would be very much greater than C infinity for dr by dt if it is greater than 0 according to this equation. That is what we can understand. Species salt must diffuse away from the moving interface. That is the reason that has to be dr by dt has to be positive. Now, the fourth question or fourth part of the problem, use conservation of energy to get a second relationship among the unknowns for salt water case. So, energy equation for liquid if you write, you get dou by dou r of r square E r is equals to 0 because E theta E phi terms we are not taking, and then r square E r should be constant upon integration. That constant is constant with respect to r, but it is function of time. So, f of t we are writing. So, but now E r here, in the previous case when pure water was there, only conduction part was there, right. Flux because of the mass transfer etc., those terms were not there. So, now those terms are being added here because this case we are doing for the salt solution case. Problem C and D are for the salt water case, salt solution case. So, this term is being added, that is sigma NIR HI bar is equals to f of t. So, r square KL dou t by dou r, this term sigma r square NIR HI bar is equals to f t. What we are writing? This sigma term also we are taking to the right hand side, right. Then dou t by dou r we are writing one side and rest all other term we are taking other side, right. So, this f of t minus sigma I r square NIR HI bar we are writing h of t. This r square NIR is constant, right. From the species conservation equation simplification previous slide, that we have what we got, r square NSR is equals to f of t is equals to capital R square NSR, this is at r comma t, this is at NSR at small r comma t. So, this is what get. So, r square NSR only for salt part we have written there, but that is true for all the cases, you get the same thing. So, that is a function of time only. So, combining this term and then writing as one simple function of time is not going to affect the further integration that we are going to do, because this entire term, though here by appearance it is looking r square term is also there. So, how can we take as a constant, because we have to do the integration next step, that you may be thinking, but that r square NSR or r square NIR is constant and that is function of time only. As per the previous slide we have done the species conservation equations simplification, right. So, this is what we have. Now, you integrate this one, t as function of r comma t is equals to h t by r k l plus constant. So, we have to find out two constants h t and then that constant. So, one boundary condition in the fourth problem, it has been mentioned that at the surface the temperature is known, that is at r is equals to capital R, temperature is known, that is mentioned in the problem, D part of the problem clearly. So, T r comma t is known, so that is T f, and then that is given in terms of T naught minus beta C s at capital R comma t. Okay. So, now here when you apply this boundary condition here, that constant should be T naught minus beta C s r comma t minus h t by capital R k l. Other boundary condition, at r is equals to infinity, t is equals to t infinity. So, in this equation if you substitute r is equals to infinity, you get constant is equals to t infinity. So, for constant we have two relations, this relation and this relation. When you equate them together, you have this relation. So, from here h t by r k l you get this one. So, we have constant as a t infinity and h t by r k l also we got it by this relation. So, h t is also known and then that constant we have written as a constant only, that is also known. So, that we substitute here t as function of r t, h t is nothing but capital R k l t naught minus beta C s r comma t minus t infinity divided by r k l is as it is plus t infinity. Fine. So, now this is t related to are function of time, right. Whatever capital R's are there, they are all function of time, but we wanted to relate this t to dr by dt. So, for that what we do? We will be doing in the next slide, by writing the balance at the interface. Okay. So, temperature distribution as function of space and time is given by this expression finally. So, use conservation equation at interface to relate temperature to dr by dt. When we do, we have Er minus sigma Ci Hi bar dr by dt I is equals to Er minus sigma Ci Hi bar dr by dt at L, liquid side and then ice side, right. So, here ice side, this Er by Er whatever is there, dou T by dou R is 0, because whether it is conduction or anything, whatever, no changes are taking place in the ice crystal side, because the temperature is constant in the entire crystal from the center to the interface. Okay. So, remaining one is that in the ice side we have only ice, no salt, nothing is there, ice crystal is there. So, minus Ci Hi bar dr by dt only we are writing without any summation, because in the crystal side we have only ice crystal, no other component is there. In the liquid side, Er is having conduction term, then whatever the energy changes because of the species flux terms, and then because of the enthalpy variations terms. And then in the liquid side we have, liquid is having both water and then salt. So, Ws quantities are there, NWR at R plus HW bar tilde plus NSR at R plus HS bar minus CW HW bar plus CS HS bar at R plus dr by dt, right. And then conduction term minus KL dou T by dou R. So, liquid side whatever are there, that those quantities we are indicating with R plus. So, at liquid side all these quantities there, when you expand this equation you get, but ice side we have only this one, all other terms would be 0, because ice is pure water crystal, okay. And then temperature variations are not there. So, conduction terms would be 0, flux terms would be 0, right, and then pure component is there. So, that is what we have, only this component of ice, only pure ice is there. So, only this part is there, right. So, now next step what we do, we write this minus KL dou T by dou R one side, and then this CW HW bar dr by dt, and then this Ci Hi bar dr by dt, that we are combining together, right, and then multiplied by dr by dt, remaining minus NWR HW bar and then minus of NSR at R plus HS bar, and then this minus of minus plus CS dr by dt term as it is here, fine. So, we have found just now in the one of the previous slide, NSR at R comma T is nothing but CS dr by dt at R comma T. So, these two terms together 0, because this is equals to this one, and then one is having plus, another one is minus. So, this is 0 together, right, and then dilute solution, it is a dilute solution. So, flux of water would be negligible, flux of salt would be higher, but flux of water would be very negligible, because it is a dilute solution, right. So, this again concentration Cw, Ci are not known, but rho W, rho I are known. So, then we are writing this enthalpies also per unit mass units. So, these remaining two terms are anyway 0. So, densities are also equal to each other. So, then rho W we are taking common, and then a problem statement, it has been given that the change in enthalpies because of the temperature variations are there very negligible compared to the latent heat. So, then this we can write rho w lambda dr by dt. Fine. So, that equation dr by dt you write one side, remaining terms, that is minus KL divided by rho w lambda dou t by dou r at r plus gamma t. Okay. This is what we have. Now, the previous slide temperature distribution, what we got? We got T as function of r comma t is nothing but T naught minus beta Cs at capital R comma t minus T infinity multiplied by capital R by small r plus T infinity was there. Right. So, from here dou t by dou r, if you do, you get that whatever this one multiplied by minus r by r square you will get, and then you have to substitute r is equals to capital R, because this dou t by dou r is at capital R plus. Okay. So, now when you do this one, so what you have? You have KL by rho w lambda r multiplied by T naught minus beta Cs r comma t minus T infinity as an expression for dr by dt. Okay. So, now next part or last part of the question is that how to compute dr by dt for salt water. So, that is dr by dt, this expression we got for dr by dt for salt water case. Okay. But how to evaluate this one? So, for that, from the part we have already dr by dt is this relation, right. Here in terms of temperature we are getting, I mean like in dr by dt related to the temperature and then r as function of time. So, it is here already we have, and then from C part Cs r comma t we have already this one. So, this Cs you substitute here, right, and then take all dr by d terms one side and then solve this equation to get the final dr by dt in terms of known quantities you will get. So, now we take another problem, effect of mass transfer on heat transfer coefficient. Here effect of mass transfer on heat transfer coefficient at interface can be approximated using a stagnant film model. Assume that there is a stagnant film of fluid of thickness delta adjacent to an interface located at x is equals to 0. Fine. Interfacial and bulk fluid temperatures T naught and T infinity respectively are known. They are given, that is at x is equals to 0 T naught and x is equals to delta T infinity. In general, there will be non-zero fluxes of one or more species normal to interface. Assume that these fluxes Nix are known constants. They are known, they are constants and they are known. Okay. Throughout the film, there are no chemical reactions in the fluid. So, recall that heat transfer coefficient is defined so that it represents only conduction Fourier energy flux at x is equals to 0 is minus k dou t by dou x at x is equals to 0 divided by T naught minus T infinity, that is nothing but heat transfer coefficient. Now, what you have to find out or prove, in the absence of mass transfer, this HTC is given by k by delta, which is a constant, because film thickness is constant, for given system k is constant. So, that constant let us say h naught. That is the first part of this problem. The second part of the problem, derive an expression for h by h naught for a general case when there is a mass transfer as well, right. So, these two problems we have to take. Pictorially, now we have an interface which is located as x is equals to 0, at which temperature is equals to T naught, right. Next to this interface there is a film thickness is delta, and then at the boundary between film thickness and bulk fluid, that is at x is equals to delta, temperature is T infinity. So, between these two limits, that is x is equals to 0 to x is equals to delta, that is within the film, this flux are constant and they are known. Okay. They are moving from x is equals to 0 to x is equals to delta side, right. So, here the H is defined like this. For first case, when there is no mass transfer, we have to find out this H is a constant. Show that H is equals to K by delta is equals to H naught for Nix is equals to 0. Nix is 0, that means no mass transfer case, the problem 1, right. So, energy equation under steady state conditions including only thermal effects, if you write dou Ex by dou x is equals to 0, you will be getting, this is a Cartesian coordinate system now we are having, and then Ex is having only conduction and then mass flux terms are there, or energy associated because of the mass flux whatever is there. So, dou by dou x of minus k dou t by dou x plus sigma Nix Hi bar, and then this variations in temperature and flux whatever are there, they are also only x direction we are taking as per the problem confinement. Okay. So, if it is 0, then from here this actually this Nix is anyway 0 for the case of problem A when there is no mass transfer. So, we get dou square t by dou x square is equals to 0, then t is equals to C1x plus C2, at t is equals to 0, t is equals to t naught. So, C2 is equals to t naught, at x is equals to delta, t is equals to t infinity. So, t infinity is equals to C1 delta plus C2, C1 is t infinity minus t naught by delta. So, now this C2 and then C1 if you substitute here, then you get t is equals to C1 is t infinity minus t naught by delta multiplied by x plus C2 is t naught, that is t minus t naught by t infinity minus t naught is equals to x by delta. Now, we need dou t by dou x, right. So, this equation dou t by dou x you do, you get t infinity minus t naught by delta multiplied by 1, and then H definition is given by this minus k dou t by dou x at x is equals to 0 divided by t naught minus t infinity, minus k dou t by dou x is nothing but t infinity minus t naught by delta and then whole divided by t naught minus t infinity is as it is. So, this t infinity minus t naught, this t naught minus t infinity cancelled out with minus. So, minus of minus plus k divided by delta. So, which is a constant, that constant we are calling H naught as per the problem statement. So, this is the first part. Exactly similar way we have to do the second part, but there we cannot cancel out this Nix because in the second case we are taking mass transfer also included in the system. So, Nix is not equals to 0, but it is constant and then constant is known, that is what it is given in the problem. So, energy equation here the dou by dou x of Ex is equals to 0 and then Ex is nothing but conduction term and then energy associated because of the mass transfer. So, that is sigma Nix Hi bar, that is also known, right. So, this equation we can, what we can do, we can divide by minus k both sides and then differentiate with respect to d by dx, then you get d square t by dx square minus 1 by k sigma Nix dHi bar by dx is equals to 0, right. So, for ideal solution with T naught as a reference temperature, Hi bar we have to define, because in general these Hi bars are not known, right, but these Hi bars are related to the CPI bar etc. So, which are known for a given system from the standard textbooks. So, that is the reason we write Hi bar is equals to Hi naught bar plus CPI bar delta T. So, from here dHi bar by dx is nothing but CPI bar dt by dx. So, that you can substitute here, then you get d square t by dx square minus 1 by k sigma Nix CPI bar dt by dx is equals to 0. This equation we have to solve, right, to get the temperature profile, then only we can get the H definition. So, now non-dimensionalizing this above equation using following parameters we are doing for simplicity of integration only. So, this x by delta we are writing as eta and t minus t infinity by t naught minus t infinity we are writing as theta, and whatever delta by k sigma Nix CPI bar which is a constant, that we are writing as a gamma. this is all a constant because Nix is constant throughout the film, that is mentioned, and these constants are known, that is also mentioned. So, that in this relation except dou t by dou x whatever is there, that entire thing is a constant one, right. So, now this when you use this expression to convert this equation in terms of non-dimensionalized variables, then we get first equation T naught minus T infinity dou square theta divided by dou square of t, you will get T naught minus T infinity dou square of theta, and then dx square you get delta square d eta square, and then minus 1 by k whatever sigma Nix Cpi bar is nothing but gamma k by delta, right, and then dt from here dt is nothing but T naught minus T infinity d theta, and then dx is nothing but delta d eta is equals to 0. So, here this k is cancelled out anyway. So, this equation both sides you multiply by delta square by T naught minus T infinity, then you have this equation d square theta by d eta square minus gamma d theta by d eta is equals to 0, right. So, this equation you have to solve to get theta as function of eta, right. So, you need two boundary conditions for theta for different eta values, right. Eta is equals to 0, x is equals to 0, that means eta is equals to 0, and then x is equals to 0, t is equals to t naught. So, theta should be 1, and then x is equals to delta, eta is equals to 1. So, theta should be, and then x is equals to delta, theta is equals to nothing but t is nothing but t infinity. So, t infinity minus t infinity is 0 by t naught minus t infinity is 0. So, boundary conditions theta at eta is equals to 0 is 1 and theta at eta is equals to 1 is 0, right. So, this equation when you integrate first you get d theta by d eta is equals to C1 e to the power of gamma eta, then second time when integrate it you get theta is equals to C1 by gamma e to the power of gamma eta plus C2. This C1, C2 are integration constants. I have written directly, you can do by steps. Okay. So, first boundary condition when you substitute, that is when eta is equals to 0, theta is equals to 1. So, 1 is equals to C1 by gamma multiplied by e to the power of 0 is 1 plus C2, and then when theta is when eta is equals to 1, theta is equals to 0. So, 0 is equals to C1 by gamma e to the power of gamma plus C2. You have two equations, two constants. When you solve you get C1 is equals to this one, C2 is equals to this one. I have written directly, you can do them, very simple, straightforward. So, this C1, C2 you can substitute here in this equation to get theta, that is this one. Theta is equals to e to the power of gamma minus e to the power of gamma eta divided by e to the power of gamma minus 1, right. So, this is nothing but temperature distribution in non-dimensional form, right. So, but we want dt by dx, because in the relation that h is equals to minus k dt by dx at x is equals to 0 divided by t naught minus t infinity, that we have to do. So, dt by dx is 0, that means in terms of theta it is nothing but t naught minus t infinity by delta d theta by d eta. In place of dt you can write t naught minus t infinity d theta, in place of dx you can write delta d eta, and then if x is equals to 0, that means eta is equals to 0. So, previous slide we just got theta as function of eta, that you differentiate with respect to eta. So, then you will get this expression, right, 0 minus gamma e to the power of gamma eta, right, divided by e to the power of gamma minus 1. Now, here eta is equals to 0, if you substitute here e to the power of 0, so that is 1. So, minus gamma by e to the power of gamma minus 1, and then remaining constant is as it is. Okay. So, H is equals to minus k dou t by dou x at x is equals to 0 divided by t naught minus t infinity k, this minus k as it is, dou t by dou x at x is equals to 0 is nothing but t naught minus t infinity by delta multiplied by minus gamma by e to the power of gamma minus 1 whole divided by t naught minus t infinity. This t naught by t infinity, this t naught by t infinity we can cancel out, and then minus and minus multiplied. So, then plus k by lambda multiplied by gamma by e to the power of gamma minus 1. So, k by delta is nothing but h naught, that we know. So, h by h naught is equals to gamma by e to the power of gamma minus 1, and then this gamma we already know it is a constant. If it is a positive constant, from this relation h by h naught is less than 1. If it is a negative constant, then h by h naught is greater than 1, right. So, that is net mass flux away from interface tends to reduce h, whereas the mass flux towards the interface tends to increase the heat transfer coefficient h according to these two conditions. If species move both direction, then relative values of CPI bar are important, because the CPI bar terms are coming into the picture in gamma definition. Okay. The references for this lecture are provided here. So, you can find these problems in this reference book, Analysis of Transport Phenomena by Dean. Thank you.